In this video, I'm going to be doing a full fluid review that's going to go over some foundational concepts as well as some more complex ideas, equations, and calculations as well. The first thing we're going to start off with is taking a look at these two containers filled to identical levels, which means that they have the same volume. Now, we're going to be taking a look at the density of each of these two fluids. Now, if we're talking about a fluid, we were talking about something that is either a gas or a liquid. When we're going to be discussing these fluids, we're talking about things that tend to take the shape of their container that are not compressible. Now, we are taking a look at a liquid in both of these cases that are sitting in these two containers. Now, density is represented by the Greek letter rho and is calculated by finding the mass over the volume. Now, not only is that the way to calculate mathematically, it's also the way to understand it conceptually as well. So when we're referring to mass, we are referring to the amount of matter. And then when we are referring to the volume, we're talking about the amount of space it occupies. So the amount of volume is basically what you're actually seeing with your own two eyes. You're seeing it fill a certain amount of space within a container, typically. Now, the amount of matter are basically the amount of particles that are packed into that space. So if you take a look at these two, there's a clear difference. You see a lot more particles or molecules in this blue liquid. Therefore, it has a higher density because it just has more matter packed in the same amount of space. Now let's take a look at this container over here where we have a bunch of molecules basically bouncing around in a container. Now the pressure that these particles are exerting on this container has to do with a couple of things. The pressure is the force per area. So force is just the amount of push or pull that something would apply. In this case, it's a push because they're basically like bumping into the sides of the container. But pressure also includes the area as well. Now, when you're taking a look at these molecules bumping into the container, it also matters the way in which they're bumping into it. This one over here, based on its velocity, because it's perpendicular to this surface, is going to be creating more pressure than a lot of these other molecules. Now, this particle coming in over here has a component that's coming in perpendicular and a component that is parallel because it has an angled velocity vector. This is the only part that's actually causing pressure on the walls of the container. So in addition to this force, we'll put the perpendicular force. A lot of times you won't necessarily have to consider the part of the vector that is applying that pressure, but in some cases you will. Now let's move on to our next case. We have water flowing through a pipe. Obviously the pipe looks a little bit larger over here and a little bit smaller in this end over here. In this case, we are taking a look at something that has a constant flow rate. The flow rate is the volume of water that's flowing through in a particular amount of time. Now, a lot of these fluid calculations and concepts all are based around a fluid that is moving through with a constant flow rate. Now, with that being said, that means that you can use the continuity equation, which is the area of one opening times the velocity of it is equal to the area of the second opening times that velocity. So we'd call this maybe opening number 2, and then this one over here is opening number 1. Now, if we have the same amount of water flowing through in a specific period of time, obviously this larger pipe over here is going to allow more water and hence has a smaller velocity. On the other end, once this area starts to tighten up, in order to get the same amount of volume moving through that pipe in a specific amount of time, it has to move through faster. So when it goes through these skinnier pipes that have a smaller area, the velocity is going to tend to increase. And this is known as the continuity equation. So quick recap of our first screen here. Density is definitely a very important property of different fluids. And again, it's basically the amount of matter that's packed into a specific space. And we are talking about ideal fluids in a lot of these cases, which means it's incompressible and doesn't have any viscosity, so there's no internal resistance. Now, when we're taking a look at the pressure of these fluids, a lot of times they are inside of containers, so they're bouncing around, hitting the walls of the container. So we're only considering the amount of perpendicular force applied to a specific area, and that's going to be the molecular collisions that add to that pressure. Now that we're looking at flow rate through pipes, we have a flow rate that's going to be consistent through these pipes, which means the same amount of volume is flowing through per a period of time, which means you can use the continuity equation showing that the product of the area and velocity at any point in a pipe with the same flow rate is going to be equal. So when you have greater areas, you have lower velocities, and when you have smaller areas, you're going to have greater velocities. Moving on, we have a couple more topics: absolute versus gauge pressure and buoyant force, which is definitely a big one for this unit. So for absolute versus gauge pressure, we have something called absolute pressure, which I would basically call your total pressure. And with that, it's the sum of your P naught plus your gauge pressure. With your P naught is basically your starting pressure, which is typically 1 atm or 101.3 kilopascals. So it's the initial pressure you're dealing with, which is typically just your atmospheric pressure or whatever initial pressure is caused by the environment. Like I said, typically one of these two numbers, depending on what unit you're in. With the gauge pressure, this is basically using rho, the density of the fluid, times G times H, and then that's basically what kind of pressure is caused by the actual fluid itself, which is either, like I said, the gas or the liquid. And then, like I said earlier as well, the absolute is summing up those two and seeing the total effects of the pressure on a particular area. So say, for example, you have a container that's filled with some fluid, and then you're trying to find the absolute pressure at the bottom of the container. With that, you have this specific height of fluid, and we'll say, for example, it's water, then you would use 1,000 kilograms per meter cubed, something along those lines, and then you would have a certain rho GH exerted on the bottom of the container by that particular fluid. But then in addition to that, because of the pressure that's normally exerted by the atmosphere, you have some kind of P naught value. And again, that would be something like a 101.3 kilopascals or 1 atm from just the regular pressure of the atmosphere itself. And then when you combine those two, that is your absolute pressure. So a lot of this stuff is basically some simple math with some adding or subtracting, depending on which one of these three you're solving for. Another example might be something like a tire filled with air, so that the air inside of the tire would be considered the gauge pressure. The P naught would be, again, one of these two numbers because of the pressure from the environment or the atmosphere, and then the total would be the sum of the two. All right, moving on to buoyant forces. Buoyant force is a fairly big topic with fluids, and the way it works is this: is if an object is placed in a fluid, so say for example we have a container filled with water again, whatever space is occupied by the actual object itself, obviously there is no fluid there. So there's some fluid that is displaced based on the volume of the actual object itself. Now the buoyant force is equal to the weight of fluid displaced. Now what happens there is we have the fluid basically colliding with this object from all directions, but the net result is that the fluid is going to have an upward force on that object, which we call typically FB for the buoyant force. And of course we have the force of gravity from the earth. If those two are equal, then the object is going to be floating at rest. If they're not equal, then obviously then the object is going to accelerate either upward or downward depending on which force is going to be larger. Now, with that being said, what you're going to do is typically analyze these using Newton's second law. And also, before I forget, this is Archimedes' principle, which doesn't matter specifically what it's called, but just the concept of it is more important. But when you're using Newton's second law to analyze these cases, we have the net force equal to the mass times acceleration. And if the object is at rest, then the acceleration in this entire side of the formula is definitely 0 newtons. So in the case that we're taking a look at here, we have the buoyant force, we'll call that an upward positive force, and the force of gravity, we'll call that a downward negative force, equals 0 newtons. And then obviously if there's an imbalance of force, then you would go ahead and leave that M and A, and then you would have some sort of A dependent on how much net force there is. Now, when working out these situations, there's a few things to keep in mind. Oftentimes, if you're finding the buoyant force, what you're doing is you're using the formula rho Vg, where that is capital V, the volume of the object. And also, one other common thing that you might use is you might use area times height to find that volume as well. So anytime you're looking for an FB to plug into some kind of setup similar to this one over here, that is a common formula that you're going to use. Now, in other instances, they may look pretty similar. You might have some kind of fluid, you might have some kind of object in there. And if it's partially submerged, then obviously then you just use that specific height of the object that's submerged along with the area to find the volume that's submerged to find your FB. But the case that I want to talk about is using the force of tension. So if something is hanging from a string and it's submerged in water, you would still do the same basic setup. You would have the buoyant force based on the weight of the fluid displaced. In this case, the tension is going to be pulling it upwards, so we have an Ft up, and then we also have the force of gravity down. So when you're introduced to a bunch of different scenarios with various forces, nothing too different here, except we have two positive forces, your buoyant force and your force of tension, and then you have your Fg counteracting those two, which you would typically solve by just doing mg, and again, that equals m times a. Okay, if the object is at rest, go ahead and make that entire side 0, and then if there's some kind of implication that it's not at rest, then you're going to plug in the mass and then solve for a certain acceleration. Lastly, we have an equation and theorem that are fairly popular. Bernoulli's equation is definitely a big one. And Bernoulli's equation is basically taking a look at the conservation of the mechanical energy. And we have two parts of a pipe that we're going to be analyzing. And you could see opening 1 over here is represented by this purple side, and opening 2 over here is represented by the red side over here. And we have a couple main variables that are in play, which is basically the height of where the pipe is at that particular moment, and then also the velocity as well. Another thing that's quite common here is because you're going to need to plug in a velocity right here, a v1 or v2, you might also use the continuity equation in problems like this, which is fairly common. Remember, the V1 and A1 correlate to the area and velocity at one of the openings, and then A2 and V2 are the area and velocity that are connected to the other one. So that might be something used in addition to using Bernoulli's equation. Now with a P1 and P2, if there's not really any pressure difference between 1 and 2, you can go ahead and cancel those out. Obviously, if there is some kind of pressure difference, you would leave them there. Now, when considering your rho GH, H could either be height, or you could call it Y as in the vertical position. Either way, they're representing the same thing. In that case, what you would typically do is call your lower position, position 0, and then your upper position, whatever kind of height you have there. Now, in the event that you did do that, then you would be able to cancel out this entire rho GH value. So considering if we had a situation where P1 and P2 were the same, you'd be basically left with rho GH1 plus 1/2 rho V1 squared equals 1/2 rho V2 squared, because this whole value over here is going to drop out because our bottom height is our base height of 0, and then you basically have some velocity at each end of the pipe as well as a little bit of height from that first position there. Now, one thing to also keep in mind is that the unit for this is oftentimes in pascals. So if you are trying to use 101.3 kilopascals, that's not really going to work for this one. You're going to have to do a little bit of converting and slide that decimal 3 to the right, which if we slid it to the right just as it's right here, it's 101,300 pascals. Technically it's 101,325 pascals. If you include a couple more significant figures. So that's something to be careful about. You might have to do a little bit converting before you place stuff into Bernoulli's equation. Now moving on to Toricelli's theorem. Now assuming if we had just 1 atmosphere above this container, it's open, and then the fluid is coming out and it's still 1 atmosphere here, it's a fairly easy calculation. What this velocity is called the speed of efflux, which is basically the exiting velocity of the fluid. Now, Toricelli's theorem basically says that the speed of efflux is going to be equivalent to as if that thing were dropped from this particular height. So going back to our conservation of energy type concepts, if we had some sort of gravitational potential energy, which is mgh, that would then all be converted to kinetic energy, which would then make the masses drop out, and then you would end up multiplying both sides by 2, and then square rooting both sides to find the velocity. So Toricelli's theorem is basically saying that if you take the square root of 2gh, then you can kind of quickly and easily find the exiting velocity of a fluid coming out of a container. Now, there are some slightly more complex cases. If you can't just do velocity equals square root of 2gh, you may have to use Bernoulli's theorem. That's usually in the event that the starting pressure and the ending pressure are not the same. For example, if you have a container, we'll say it's sealed, and you have 2 atmospheres up here, and then it's coming out to a regular 1 atm over here. Then what you're going to need to do is you can go ahead and use Bernoulli's theorem and say that we have a P1 plus a rho GH. Okay, we don't have any initial velocity in the beginning here, so we can get rid of this 1/2 rho V1 squared, and then P2 plus, and then we can get rid of the rho GH2 here now that it reaches its minimum height within the container, and that equals 1/2 rho V2 squared. And then in that case, you would basically solve for the exiting velocity right over here, except you would just use (101,325 pascals), this one times 2, and then this one just 101,325. And then you would just then input the rho, g, and h, and then the rho one more time, and then mathematically solve for the velocity. of the fluid using Bernoulli's equation. So Torricelli's theorem is kind of like if everything is all set up nicely, then you have a nice quick V equals square root of 2gh type setup. If there's some difference in pressure, then you're going to have to go ahead and grab Bernoulli's equation. You will be able to do some canceling, and then from there you could still find velocity using a setup that generally looks sort of similar to the one in red I have over here. So I hope that helps in summing up a lot of the main fluid concepts. If you have any more questions or need some clarification about setting up some of these calculations, make sure you head to the Beat Physics page, check out the fluid folder, and there's a bunch of different examples of how these calculations are completed. Thank you for watching and listening.